Swayam Prabha. Digital India. Educated India.
Primarily about the Gibbs-Duhem equation. This is actually applicable for any extensive property. What we have seen is, for any extensive property, I think I will write everything in terms of specific properties, sorry. Okay, where E is identically capital E by N, by the total number of moles. This is one equation. The other equation says, I will say example binary. We will discuss binary mixtures and then I will extend it to multi-component mixtures. E is equal to x1 then we showed that, or this is 1, this is 2. Since Gibbs-Duhem equation says two follows from 3, from differentiating 1 and using equation 3. So we have the simple result that I can solve equations 1 and 2 simultaneously for E1 bar and E2 bar. So I have E1 bar is equal to E plus x2 partial of E with respect to x1. And then E2 bar is E minus x1 partial of E with respect to x1. Just switch 1 and 2, but differentiation with respect to 2 is same as differentiation with respect to 1 with a minus sign. So this is the set of, this is the simplest way of solving for E1 E2, and it has the advantage that because there is 1 degree of freedom, this has the advantage that these equations are symmetric. You can simply model E and you do not have to model any one of the components. So if you have a model for E, then you automatically have, these are general results, these are very important, and in particular the most important, in fact there are 3 quantities that are important. I will say E equal to G, which is the most important thing, G, H and V. These two are measurable, and this is important from a theoretical point of view. you know that G by T with respect to T will give you minus H by T squared, G with respect to P will give you V. So the pressure dependence and the temperature dependence are covered through measurements of H and V. Because enthalpy and volume are also extensive properties, these conditions are satisfied. So if I can measure enthalpy change, for example, actually I should have written this, I wrote I think everything as, let me make a small change here. I should actually have written everything in terms of delta E, which is what I did last time, right. I will just repeat it here, I will say more conveniently because what I have written there is correct. We write the same equations, we write equations like this: delta E is equal to sum over xi then you get partial of delta E with respect to delta x1. I have to write it for specifically for binary. I am just repeating the whole thing for just 1 second. Hello. You guys, I don't know what to do about this chikungunya. Apparently some cases in the campus because public health officer, and he said he was doing it. Okay, I'll double check it. Otherwise, why don't you tell the wardens? I'll also tell the wardens. We'll make sure some spraying is done. This thing is not fatal, but apparently it causes near unbearable pain in the joints for about 3-4 days. Okay, we'll come back to this. I am rewriting all these equations. So these are not new equations, but these are equations written. This will be 1 prime in terms of mixture properties. So this is E1 bar minus E1 minus E2 bar minus E2. Okay, and then we have E1 bar minus E1 is equal to delta E plus x2 partial of delta E with respect to delta x1 and so on, and then 1 and 2 can be interchanged. What you are looking for is this property here, E1 bar, because if you are doing phase equilibrium, we have already shown in particular, remember that G1 bar is the same as mu1. So we have shown in phase equilibrium that mu1 alpha is equal to mu1 beta, mu2 alpha is equal to mu2 beta governs the phase equilibrium. So if I know the chemical potential as a function of composition, then I can do the phase equilibrium calculations. So the purpose of this entire exercise is to get the composition dependence of the chemical potential. Since it is more general than that, the theory actually applies to all partial molar properties. I am deriving it in general for an arbitrary partial molar property. I said 3 are of importance: delta G, because that will give you the chemical potential as a function of composition; delta H, delta V, because they govern the temperature and the pressure dependence of the chemical potential, and those are the measurable quantities. These are not actually what is measurable is the change in enthalpy and the change in volume. Volume of course is explicitly measurable. So we have these equations. So what we have is, in particular, when E is equal to G, E1 bar is equal to mu1 and E is equal to H, E1 bar is equal to, I am sorry, H1 bar. For the others we do not have a name. This is G1 bar, which is identical with mu1. Yeah.
Minus small ei.
Because E after mixing is xi ei bar. We integrated the basic equations to show that.
Fine, sir.
You remember?
Initially.
Otherwise I can recall it for you here. Do this here. We did it for G. The basic equation simply tell you this quantity holding T P N J not equal to I is called ei bar. That is the definition of partial molar property. We integrated this at constant T and P, but at arbitrary T and P the initial state was characterized by T, P and some composition, and we took this thought experiment in which we expanded the system by a factor of k and to calculate the differences. From that we got E is equal to sum over ei bar Ni. So for property of a mixture, it is not sufficient for you to know the specific property of pure I, you have to know its value, the per mole value in the mixture. This is a function of composition. This is also equal to E after mixing. If I am considering a process, this is identical with E. E before mixing is sum over Ei Ni. This Ei is pure I. I take n1 moles of 1, its value of E is small e 1, so I just add it all up because this is before mixing. After mixing, in the mixture the property changes from Ei to Ei bar. So if I want to understand the mixing process, I have to know how to calculate Ei bar. That is the central thing in mixture theory. Of course it was not done this way, actual science progresses by iterations by various things, but since this is 175 years since all this was done, in fact more, I think 1927 or something, I forget exactly, when people started doing this process, when Gibbs introduced partial molar properties and so on. So it's been refined over a period of time. Now we see it in perspective. The way we look at it is simply to look at the process of mixing, in which you can make measurements. You can mix two components at constant T and P. The quantities you can measure are actually delta H and delta V. You can't measure delta G, but it so happens that delta G is the most important quantity because it governs phase equilibria, chemical equilibria through equality of chemical potentials in two phases. So I have to look at delta G, although it is not measurable. Delta H and delta V are measurable. So I am looking at E before mixing, E after mixing. If I take the difference between these two, you get Ni into Ei bar minus Ei. If I take per mole of the mixture, I get this equation here. I take x1 moles of 1, x2 moles of 2 and form 1 mole of the mixture. So per mole of the mixture, the change in E is simply given by xi into this. And I am doing binaries because primarily we will be dealing in this course with binaries. Then I will show you that the extension to multi-component systems is trivial, it is only algebraic complexity. In practice though, if you went to a refinery, they will tell you, you guys are being theoretical, the actual refinery has 21 components, but all you have to do is extend this and hit the idiot box on the head, I mean the computer. You just have to hit it on the head, it will give you spit out all the answers for you. Just simultaneous equations, instead of solving 2 equations you will solve n equations in an n component system. They are all absolutely trivial. In principle this is all there is to it. But what we found from thermodynamics also is that the equations for the chemical potential, or for EI bar for that matter, for any EI bar, you have n variables and only n minus 1 equation. So there is 1 degree of freedom. Thermodynamics cannot give you that degree of freedom, there is uncertainty. So that comes from experiment. The only way to do it is try and measure, use something, experiment or empiricism, you guess a model, either modeling or experimentation. For delta H, delta V you can get it from experiment. If you can get it from experiment, you do not do modeling. When you are uncertain you do modeling, you start talking about way mixtures occur. Classical thermodynamics does not provide you with any method for calculating this directly. Molecular thermodynamics gives you mechanisms, because there are molecules, you can say this molecule is replaced by this molecule. For example, if I want to talk about mixing, I will imagine a box full of molecules of type 1 and I will bring a molecule far away from infinity, molecule 2, to the middle of this mixture. Then I ask what is the configuration around this molecule 2, what was the configuration before, what is the difference in the energy, and what is the difference in the entropy. I can do these calculations in molecular theory, but as far as classical thermodynamics is concerned, I am simply guessing what delta E is in the case of G. In the case of H and V, so I will say for E equal to H or V, use experimental data. For delta H, delta V. For E equal to G, models have to be developed. We have exactly one model, one ingenious model. And variations of that. This was done in 1898, as I told you, by Van Laar. I do not know if the Dutch say read V as F, the Germans do, but I am not sure. I have heard only Van Laar here and in the US, so I have to check with some Dutchman, and I will say parenthetically van der Waals. And then any number of molecular models. And then empirical models, of course. You will have to know the Van Laar model. For one thing, it works very well and it is also beautifully derived. I will derive it here. You do not need any extraordinary concepts. With the existing concepts you can do the derivation. It is a really clever one. I mean, after it is derived you can say what is the big deal, I could have done it, but it is. If you go back 1898 and look at the state of thermodynamics and ask if you could have guessed it and you said yes, then you had better be jolly good, you better be Nobel Prize quality. But if you are honest, most probably you will say no, you could not have even thought of it. Molecular models, there are many of them. The ones you have to know in this course are all of these are actually quark first, if you like, it is not, then uniquark, then there is a model called NRTL, then I should have mentioned Wilson. I think those are the only ones you will have to know. There are more, but these are the tested ones, and empirical models starts from what is called Porter's model, Wohl's models. He has a whole series of models, and I will add Van Laar again, because Van Laar is actually derived of very good model. It had only one parameter in it. Then people didn't, later people who came along used his equations without realizing that there was only one parameter. There were two parameters were related to one another. They didn't realize it, so they made it a 2 parameter model, and the 2 parameter model is so successful that it is fully established. So we will use the empirical model of von Lahr, which is the same model as what we derive here, except that people forgot how it was derived. And, this kind of thing happens all the time. And then finally there is a model by Dolzalek. No, that should come under theoretical models. I will say here von Lahr, one classical model. I suppose I should say, I will also say plus one due to Dolzalek. This comes under, it's slightly different, it comes under what is called chemical theory of solutions. All of these come under so called physical theories. That means these theories for mixtures are derived without assuming any chemical reactions. Dolzalek said all mixtures are ideal except that you are looking at the wrong species. So therefore it is a chemical theory. It assumes, it postulates chemical reactions that actually occur in mixtures, as a result of which if you mix A and B you do not get a mixture of A and B, but you get an ideal mixture of A2B and AB3 if you like, some combinations. He postulates that there are reactions that take place in the solution. In the final mixture, if you looked at the right components, is simply ideal, but all others are physical theories. Actually there is some evidence for chemical theory. Chemical theory is now used in all cases where there is clear evidence of association, solvation. We have mixtures where the components in solution form dimers, or for example HF in a mixture it always seems to exist as H6F6. If you take that into account, then it does form ideal mixtures with other substances. Similarly you have solvation where a solute molecule is surrounded by the solvent molecules because of high interaction. So if you take that complex as one entity, then you have an ideal mixture. So these are very special cases. Other than that, these are the models. I will just say a few words about these acronyms. This is actually called quasi chemical theory. It is called quasi chemical theory because the form of the final result looks like the result you would have got had you assumed a chemical reaction. It sort of recalls Dolzalek's theory, but there is no chemical reaction postulated here. The reaction postulated is of this form, I mean postulated in the sense the final result looks like it, in the sense that this was done by Guggenheim, that is the big name here. There is a series of Guggenheim lectures, Guggenheim this thing in Europe, because students all combined to form these lectures and they are very prestigious. Anyway, Guggenheim suggested that if you take a lattice model for the, and you do not have to go to molecular thermodynamics for this, you simply imagine that 1 and 1 are neighbors, and he says if you have a 1 and 1 and then a 2 2, this is 1 1, this is 2 2, in the mixture you are replacing these 1 1 bonds by 1 2 and 2 1 bonds. The 2 2 and the 1 1 are you breaking up and you are forming 1 2 and 2 1 bonds. Simply did a counting on that and assumed that 1 1 plus 2 2 produces 2 times 1 2. If you imagine the reaction of this kind where you go from a 1 1 pair and a 2 2 pair to 2 1 2 pairs, then you would write a chemical equilibrium equation which tells you the number of 1 2 pairs whole squared by the number of 1 1 pairs times the number of 2 2 pairs is equal to constant. That is the equation that comes out of the theory, and therefore the theory is called quasi chemical theory. This is called the universal quasi chemical theory. This was derived by Prausnitz. So I will write the names down. This is Guggenheim, and then this is due to Prausnitz and co-workers. Prausnitz is probably 75 and he is at Berkeley even now. NRTL is again due to Prausnitz, but the name associated with okay, I will tell you for Uniquac the name associated with that is Abrams. For NRTL it is Prausnitz and Renon. Wilson is due to Wilson. So he generalized, Prausnitz generalized this theory, again made a mistake, ended up with two independent parameters that correlated data so well that you can't argue against Uniquac. I mean, if you say Uniquac shouldn't be used, people laugh at you. Then further corrections have been made. In fact, we ourselves have made the correction in Uniquac. There was a mistake. So we have got to what is called the it's not yet widely used, there is no point in teaching it in an undergraduate course, but it's essentially a self-consistent theory. NRTL is actually, again I do not want to get you guys to get very skeptical, NRTL is derived by a mistake, but the resulting equations correlate data so well that people have accepted it again. It is called non-random two liquid theory. There is a corresponding theory, actually I must have mentioned that here. Apart from these, there is another whole list of theories that go by the name of corresponding states. I will discuss that separately. There was a corresponding states theory due to Scott and what from that theory this NRTL theory was derived. I mean, that as a basis. I am going to discuss all these in greater detail, just giving you general stories behind it. But anyway, this theory is a very successful theory for liquid mixtures. So we will use it. Wilson is the guy who started the whole concept of liquid mixtures, theory of liquid mixtures. Actually, it was a very small paper in 1962. I think it is in, if I remember correctly, in Journal of JCP, and it was a very small one-page paper, and Wilson simply said, maybe I am jumping the gun, but let me say this a bit. Suppose you have 1 1 1 1 1 here, and then you introduce a molecule of 2 here. What he suggested was, for example, this could be suppose you looked at a liquid mixture closely and locally you could take a look at, let us say this is the lattice configuration. I have 4 neighbors arranged like this around a central molecule. Actual lattice configurations are different, but it does not matter. I am only illustrating a point. If I have cells like this inside the liquid, then I have a 50-50 mixture of 1 and 2. All around, all it sees is neighbors are 1s, and here it is 2. And I will show you the following physical result. We have already seen this result. You have seen that the work done in a process, in an isothermal process at constant temperature and pressure, the work done is equal to minus delta G. We saw that for open systems. Correspondingly, this number, the work done in bringing a molecule to 1 mole of 2 into, or 1 molecule of 2 into a mixture of 4 molecules of 1 and so on, is determined completely by the chemical potential mu2. I will show you that mu2 is the change in mu2 from the pure state gives you the work done in bringing this molecule to from infinity to here. That is the physical interpretation. So the work done in this mixture, in a 50-50 mixture, is actually not dependent on the global composition but on the local composition. So what Wilson said was, you should not be talking of x2 but you should be talking of x21. That means the mole fraction of 2 in the neighborhood of 1, and that is what determines the work done, and that is what determines delta G. That started off a whole spate of theories called local composition theories, and all these come under local composition theories. This does not quite come under local composition, it was derived before Wilson's theory, but Uniquac and NRTL come under local composition theories. All these, so these 3 are called local composition theories. I think that is all as far as these theories are concerned. What I will do now is derive the theory of Van Laar. Van Laar basically said, I am interested in a model for delta G. I want the composition dependence of the free energy of mixing. This is clearly equal to delta H. You are doing mixing at constant T and P. This is the process of interest. I am looking at delta G mix, it is equal to delta H minus T delta S. This is equal to delta U plus P delta V minus T delta S. Constant T and P, so at delta T delta P will not come in, no change in temperature and pressure. Of these, this is an argument, you can make the change, but this is a valid argument. For a large number of mixtures, the change in delta V is so small that P delta V is very small compared to delta U. So I am going to neglect this because it is small. It is a reasonable assumption, very rarely is delta V large enough for you to worry about. It is an assumption that is made very often. Then he said I am going to have an ideal mixture. I already understand an ideal mixture. I showed you that one solution to the Gibbs-Duhem equation is log x1, but let us say I assume delta G ideal is equal to delta H ideal minus, so I will say approximately, in fact I will say equally, minus T delta S ideal. Here I can write P delta V ideal also, but in the ideal mixture there is no change in volume, there is no change in enthalpy. I do not have to worry about those. In an ideal mixture you have molecules that do not, whose interactions are not different in the mixture from in the pure state, so there is no change in enthalpy, there is no change. So this difference delta G minus delta G ideal is equal to T delta U, and write minus delta U ideal, but this is actually 0, minus T this is written identically as G excess. Similarly this will be written as U excess, this is written as S excess. The superscript E is for excess, it means over and above the ideal case. All theories, the molecular theory or the classical theory, so far we have a problem with finding both. They either assume U excess is 0 or S excess is 0. I must say one more model here. In the molecular models there is one more model which is due to Flory, called the Flory-Huggins model. It was polymer solutions, where he said the big difference is not in energy but it is in arrangements. So if you put in one polymer molecule here, the polymer molecule is so large that it has about 10,000 neighbors. So your actual polymer concentration will be in parts per million, but it will have a tremendous influence on properties. It is sort of deceptive. If you take the weight fraction, the polymer will be very high, but if you take mole fractions, the polymer will be very low, because the polymer molecular weight will be 100,000, the other molecular weight will be 10, so the a factor of 1000 or 10,000. So he was looking at special case of polymer solutions and he derived a theory that's, it's a beautiful theory, but it's one of the earliest as far as, so Flory is another person you should remember. It's called the Flory-Huggins theory, Huggins was a student. But anyway, coming back here, all theories, Flory for example said U excess is effectively 0, it is negligible, it is the entropy change that is most important. And many other theories assume that S excess is 0, that means the mixing is ideal but the energetics are important. So Van Laar for example said, Van Laar's assumptions are the following: assumed first that delta V is approximately 0, it is a very valid assumption. I will say valid almost always. And then he assumed Sxs is equal to 0. This is not always valid. Certainly not valid for solutions of mixtures of substances that are very different in size. But this is not always valid, I will say, for example, not valid when sizes differ significantly. So he finally said, therefore delta G is equal to delta U. You can relax some of those assumptions, it is not trivial, but you can. But you are now going back in 1898, he went back to this equation, he did not do it exactly like this. This is also equal to Cv so he starts with this equation, du is equal to, you are talking of constant temperature process, so this is 0. And the real interest was in mixing of liquids, that is of interest even now in thermodynamics, because in mixing of gases not much happens, gases behave reasonably well unless you are talking of very very high pressures. So what van der Waals then did a very clever thing, he said he wants to mix 1 and 2, let me say x1 moles of pure 1 and x2 moles of 2 separately in 2 boxes. From here you have to go to mixture of 1 and 2 of composition x1. This is liquid, this is also liquid, and you want to know what is delta G. The progress we have made is delta G is the same as delta U, but I do not know delta U yet. So I have not made much progress. What he said was, at this is at pressure P, at T P, this is also at same temperature and pressure. He said he will go here to T comma P is equal to 0. He will simply, this is a thought experiment. So you just imagine that you evaporate completely 1 and 2, go to P is equal to 0, you have to be below the critical temperature, otherwise, actually for this you do not, I am sorry, let me just get back here. So you just go to P is equal to 0, then you mix the two, this is ideal mixing. So you produce a gaseous mixture of 1 and 2 and then you condense it. So this is evaporation, this is condensation. So you are replacing mixing, this is ideal mixing, this is mixing. So the process of mixing you replace by evaporation, ideal mixing and condensation. Now he is looking at it step by step. If you look at this, you want only delta U for each of them, delta G for this is the same as delta U, delta G for these 3 steps, because G is a function of state, delta G, it does not matter if I calculate delta G from here to here or from here to here and then to here and then to here, and I add these. So we will call these A, B, C, D. So first is delta G A to D is equal to delta G AB plus delta G BC Now he said you can replace this by delta U AD Actually he did not say this, sorry, this is delta U minus T delta S, please correct this, but he said G XS is equal to U XS, because delta S for the real process he said was the same as delta S for the ideal process. The ideal process entropy you still have to take into account. I think I am going to stop here and repeat what I said, because I have said a lot. I will continue next class. Actually the calculation steps are fairly straightforward, but imagine first of all the quantity of interest is the chemical potential for all phase equilibrium calculations, for reaction equilibrium calculations also, because on the one hand for reaction equilibrium I am going to use the fact that G should be a minimum, and G again is given by Ni mu I. So if I know mu I as a function of composition, then I can play games with this. If I want G to be a minimum, I use the usual calculus, but I have to use it in terms of measurable quantities, so I have to express G is equal to Ni mu I in terms of composition variables. So I need chemical potential as a function of composition. Now thermodynamics will give you the temperature dependence of the chemical potential through the enthalpy measurements, it will give you the pressure dependence of the chemical potential through volume changes measurements, but it cannot give you the composition dependence except through the Gibbs-Duhem equations. The Gibbs-Duhem equations, as I told you, constitute n minus 1 equations for n variables. So there is 1 degree of freedom. The way to deal with the degree of freedom is to look at the mixing process and derive all the results in terms of change in G during mixing. So that is all I have done. Instead of looking at change in G, I looked at change in any extensive property, because in particular I am not only interested in change in G, I am also interested in change in enthalpy and change in volume. The change in G is given by, we derived those expressions, and you know how to get E1 bar, E2 bar once I know the change in G. I have to know change in G as a function of composition. So that is all I am looking at. What Van Laar said was, we do not understand liquid mixing, it is too complex, but we understand ideal gas mixing. So he will go from here, evaporate this. In order to evaporate this, all he has to do is integrate this from P is equal to 0 to P is equal to P, right, or the other way around, P to 0. If you integrate this, you just write this as dou V by dou P dP and integrate it. If I have an equation of state, I can calculate all these quantities, right. It is not ideal, after all you are going on increasing the pressure, it is going to be non-ideal. So you put in the van der Waals equation of state for P, do these differentiations and get this difference. In particular you will get A by V squared, van der Waals equation says P plus A by V squared into V minus B is constant. So when you do P with respect to T, you will essentially end up here with A by V squared dV. So if you integrate that, you get directly a nice expression. In terms of A, you will get delta U. So the change in internal energy here is measured by that constant A11 for pure 1 and A22. It has got two subscripts, because in a mixture A changes. Then you do the ideal mixing, there is only entropic change when you do ideal mixing, and calculate that entropic change separately. So delta S ideal is known, delta U ideal is 0. Then I have to do this calculation. For condensation, again van der Waals equation had to be used. It is a mixture, A and B are functions of composition, and what functions of composition, you have to use an empiricism there. I know how mixing occurs for hard spheres. For example, the size of the mixture here is treated as if it was one molecule or one substance with certain parameters, certain size and certain energy. So here again van der Waals already had mixing rules, we will use those mixing rules and calculate the condensation energy. It will also come out in terms of A mix. So the whole process, this plus this will give you this expression delta G. Once I have delta G, I can get mu1 mu2 by differentiation. We have already written those equations down.